Hi. बंद कर दो इसको. So while the mic comes up, I will come closer to you and speak. So what were we doing in the last class? Who can remind me? NAND. What is NAND? वहां से flash एक अलग शब्द आया, तो दोनों को जोड़ के NAND flash. We're doing NAND flash. So what is NAND flash? So you're saying that we program, so it's a non-volatile cell, first of all. What does non-volatile mean? That even when the power is turned off, we will still be able to store the contents. So even when power is turned off, we will be able to store the contents and retrieve them much later. What is the life of contents stored in a flash memory? Infinite. 3 to 5 years. So I say something on the NAND memory today, for 3 to 5 years, you say it will remain there. So मैंने तो आज एक hard disk ली. I pick up a hard disk today and I keep backup and I keep it aside. Just one program cycle. It will stay there for 5 years. Asking, will it stay there for 5 years? So Dipank is saying ideally it should, but why but? किसी को कुछ नहीं सुनाई दे रहा. So what he's saying is that there could be some environmental variations like temperature and temperature is the main thing. Okay, so temperature and high energy particle strikes, electromagnetic variations in the vicinity, because of which electrons could move in or out of those trapped, the floating gate, due to which you could lose data. But otherwise, if nothing of that sort happens, you can actually say that if you store something in a flash memory, it will stay for life. 5, 10 years, whatever the life of that memory is, it will stay there. But so this is the non-volatile characteristic of a flash memory. What about this endurance thing? You're mentioning something, कुछ लोग यहाँ पे बात कर रहे थे endurance की. What is that endurance thing about? How many times you can read write into the memory, huh? So how does that change? How is it different from, let us say, a SRAM or a DRAM? And why is it different? अरे मैं बोल रहा हूँ. Hello सुनते रहना बाद में. Thank you. अखिलेश, लाइट भी ये वाली कौन सी है? Clear है? Okay. So endurance. What is this endurance about? The number of time I can do read and write. Why is it different for a flash than it is for an SRAM or a DRAM? VT is changed. So to be able to change that VT, we are applying high voltages. In a NAND flash, we are going to voltages of plus 18 volts. We saw in the slides, 18 volts, minus 10 volts. पता नहीं कितने तो voltages लगाते हैं आप, है ना? So when you apply such high voltages, the gate dielectrics, even though they are thicker than the regular gates, they degrade. And then the breakdown can happen. And that is what limits the total number of cycles, total number of stores and erasers that you can do on a flash. How many? What is the typical endurance? Typically 10,000 cycles. So is it good enough for your storage applications? For a flash card that you have, for a for your phone memory, it is fine. 10,000 times. How many times will you read, erase or and reprogram the same cell? How many times do you erase a file? Once you've loaded a file on your computer, how many times do you erase it? 10 times, 20 times, 30 times. We are saying 10,000 cycles. Good enough. Much more than good enough. How many times would you format your memory? 10 times, 20 times. We are saying 10,000 cycles. So for solid state storage, flash is a perfect solution. Very high density, can store contents for 5 years, 10 years, whatever duration you want. And for the practical purposes of the application, it also endures, works. Then why not for L1 cache or L2 cache? If I want to use a regular flash for an L1 cache, what are the constraints there? So first thing is speed. Flash is much slower than regular SRAMs. So first is speed. Then what else? Okay. So see, the cache memory would typically operate at the same frequency as the processor. L1 cache will definitely operate at the same frequency. L2 cache can probably operate at a frequency which is lesser than the actual frequency, because L2 cache you do not access as often, and you can anyways take an extra cycle or two to access the L2 cache. But it is still the same order. If your processor is operating at 2.4 gigahertz, so it is talking about 2.4 into 10 raised to power 9 cycles per second. Even if I say 1% activity rate, I still have 2.4 into 10 raised to power 6 per second, 7 per second. एक सेकंड में आपकी फ्लैश की एंड्योरेंस लिमिट खत्म. If I say that I can somehow make it operate at that kind of a frequency, even then the endurance prevents it from being used as a L1 cache. And that is where flashes are not considered as universal memories because of the endurance limitations. And that is why in the last lecture of this course, we will look at other memories which could probably be called as universal memories, even though, not exactly universal memories. So you may hear lots of hoo-ha about, oh, memory design, there's no future around it because flash will come or something else will come and that is going to be the universal memory. Why are you designing DRAMs? Why are you talking about SRAMs? And when we will look at those places, we will see that a universal memory, essentially what they are saying is that it is a memory which could be used on chip, which could be used off chip, both places. That you do not need a main memory like a DRAM. That same memory could be used for as the main memory also. That is what universal memory means. Probably it could also replace L3 cache on your chip, an SRAM which is operating at which is very high density SRAM on a chip, a huge capacity. You could replace that also with that new universal memory architecture. But to be able to replace an L1 cache with that one, there are many barriers to it, at least yet. And it can happen, it may not happen. What we definitely know is that they will coexist for a long period of time. SRAMs, DRAMs, flash, or whatever other NVM architectures will come up with, they will coexist for a long period of time. That is what we are definitely sure of. Okay, so you attended Kalyan's lecture last time. Any questions from there? How was it? Insightful. Okay. You like one thing that was very clear was that whatever we discussed in terms of basics, they remain same. We still had a floating gate, we still had a control gate, we still had all those things. What changed? The implementation. When we were looking at the theoretical, the bookish slides hain, usme kya dikhta hai? That everything is planar. But when he showed that you have pillars, and on one pillar you have 176 word lines coming. So you realize what we're talking about? The entire thing is 3D today, and no book would ever have it. And this is such information which only you can, which we can bring to you only through such guest lectures, nowhere else. So any questions from there, Kalyan's lecture? That is another architecture of non-volatile memories, are RAMs, resistive RAMs. So there we use a device which is, you may say, a oxide resistance, matlab multiple implementations hai, but yeah, some resistance, which would be we will see in the last lecture. Don't worry. That's again a non-volatile architecture. Presently, all those non-volatile architectures have their own sweet spots and constraints where they cannot be used in other places. But over time, a few of them will emerge as very strong candidates and candidates to replace flashes. Any other memory also, why just flashes? Nothing? Okay. So see, what we have done in this course till now is we started with SRAMs, SRAM cells in particular, studied them in much detail. We studied about different constraints, sizing constraints. Even though it's just a 6 transistor cell, we now realize it is not a piece of cake. To design this 6 transistor cell, a lot of effort needs to go in, a lot of design constraints have to be met. So that thing is evident to all of us. Then we looked at periphery circuits around the storage array. We looked at the IO design, we looked at the row decoder design, address decoding, multiplexing, IO circuits, sense amplifiers, all of that we looked at. We looked at verification aspects of a memory, where we talked about Monte Carlo, we talked about race conditions and how these race conditions have to be met at all times. Remember? Then we looked at sources of variations. Because when we talk of such huge capacity, so many transistors on a chip, and we want good yield out of it, then variations are something that we have to be extremely careful about. We have to account them in all our verifications. We looked at the sources of variations and process capability parameters like CP and CPK. Kisko yaad hai itna, Afridi? This is 2 months old story that I'm revising for you. How many of you remember parts of it? How many of you remember most of it? So parts of it? Okay, most of it? All of it? Okay, so you better remember at least most of it, not for the final exam. No, abhi tak jitna maine bataya, that was all pre-mid-sem exam. Not for the final exam, but you better remember all of it, because most of you will be sitting for placements pretty soon. So ask your seniors. DVD and MDT, these are 2 courses जिसके अंदर से बहुत सारे सवाल आते हैं in the interviews. Not in the written test, but in the interviews, they will ask you many questions from these. And those questions are not superficial, by the way. They are reasonably in-depth, involved. They would twist the facts, they would twist something, and they would ask you stuff. So you better be prepared, have a good understanding of. So we have all the lectures recorded with you, so don't miss out on them. It's important, and you will see that the interviewers will definitely ask you questions around MDT also, especially those from Synopsys. They come to hire memory designers. They will definitely ask you questions around MDT. So do not just thoda sa yaad hai se kaam nahi chalega. When they ask you some questions about, you say, I have done a course on memory design. I'm bound to ask you questions on what is a memory cell, how does it operate, what are the figures of merit, how do you design it. So you're working on projects already, many of you. You will get hands-on experience around that. But those of you who are not working on memory cell projects also, you should refresh your concepts and get up to date on that. Okay. So once we did this SRAM design and SRAM ke around ke constraints, we moved to the next level. What did we talk about? इतना मरमर्स आ रहे हैं, किसी को याद ही नहीं है, मतलब तुक्का मारा जा रहा है, कैशे था क्या, कैशे था. So we looked at, we went to slightly higher level of abstraction. We said that, okay, SRAM एक बार आपने design कर लिया, you do not use it as is. There is a hierarchy in which you use it, and then we talked about L1 cache, L2 cache, and the hierarchy there. This was also pre-MITSEM. Then we moved to DRAMs. And DRAMs, so okay, why did we spend so much time on SRAMs and then just 2 lectures on DRAMs, just 2 or 3 lectures on NVMs? Why did we do that? Why did I not spend equal amount of time on DRAMs and then equal amount of time on NVMs also? Yes, because the framework is the same. You have some, you have decoding in SRAMs that we discussed in detail. We saw different kinds of decodings. We saw bank architectures, page architectures, everything. So now I do not need to teach you all those things again. So the concepts that we learned in the first part of the course are anyways being involved and used in the second part. We're not repeating them again. There's no need. What do we talk about? We talk only about those things which are different from SRAMs. We talked about the capacitor implementation in a DRAM. We talked about the trench capacitor and how it is non-scalable. We talked about leakage and the refresh rates of the DRAM. We did not talk about how the sense amplifier needs to be designed. Okay, you simply said there is a sense amplifier per bit line. That's good enough. We looked at replica design instead, because the replica or the reference bit line design is more important. That requirement was not there in an SRAM because we were talking about differential SRAMs in the first part of the course. But then it is definitely relevant for the DRAM. Now, this reference bit line design part, is it only relevant for DRAMs, or there could be some SRAMs which could also benefit from that session? Sorry? So replica bit line, we use them in SRAMs also. But in what we studied in DRAMs was a different kind of it was not a replica bit line that we studied in DRAM. We talked about the reference bit line. Every sense amplifier has this reference bit line for it. Is it involved or is it important for other SRAM, for some other SRAM architecture also? Very good. Very good. So there are SRAM cells which have only single bit line on the read port. There again, for the sense amplifier, you will need a reference bit line. And what we studied in DRAMs fits in there. We studied about charge pumps. So are there charge pumps that we use in SRAMs also? Negative bit line architecture. So चाहे हमने उस concept को DRAMs के context में cover करा, but the same thing, the same concept is applied in SRAMs also. So do not think कि SRAMs base था, उसके बाद की जो चीजें हुई वो खाली DRAM में आई. नहीं नहीं नहीं, जो हमने बाद में करी वो SRAMs के लिए भी applicable हैं. Okay, so it is not कि हमने बस SRAMs को छोड़ दिया पीछे, ऐसा नहीं हुआ. हमने कुछ concepts SRAMs के आगे जाके भी cover करे, so that, but we covered it in the scope of DRAMs because for DRAMs it is much more involved and much more relevant. A charge pump, the way it is in DRAMs, is a completely different league than what you would draw for a SRAM, negative bit line. But the same concept you will use, a simpler one, a simpler implementation on the other hand. And then we looked at the flashes. After DRAMs, we looked at flash memories. We looked at the requirement for high voltage. We looked at when Kalyan was talking about error correction codes, the ways in which MLCs, multiple level cells, and these are made functional in the first place. So you do not mind giving some extra area because you are actually increasing the density of your memory cells significantly much higher. So all those concepts are kind of with us now. Today, what we are going to start is how to test all of this. आपने अब डिजाइन कर लिया. Designing is half the story. Unless you are able to test and verify and say that whatever I had designed is how is it available on silicon also, doesn't work. So we'll now start to look at testing. What do you mean by testing? Why is it important? We discussed this in DVD also, but just a refresh. Why do we need testing, and why is it important? Ensure the functionality. Just functionality? So we are shipping the products to the customers. Before shipping, we have to be assured that they are functional. Pala is adding specification should also be met. It's not just functionality. Functionality is one aspect of it. But I cannot sell a cell or a memory which is 10 times leakier than what I had specified in the data sheet, is it not? Or which is 50% slower. आपने कहा कि मेरी memory 1 gigahertz पे काम करेगी, it will operate at 1 gigahertz, but finally it's operating only at 500 megahertz. You can't sell it to the customer then, can you? It will naturally fail. So functionality is not the only thing that we want to test. We want to test performance also. We want to test other parameters also, which we have committed to the customer. And it is very important because if those parameters are not met, even if the memory is functional, it will fail on silicon. It will fail in the system in which it is embedded. So what kind of tests do you remember we do on ICs? Forget memories, Abhi. What kind of tests do you remember? Remember that we do on memories. Okay, so there are accelerated life tests. Okay, and built-in self-test. Okay, that is a test. That is a built-in, matlab built-in hai, but what is the test? So you're saying at speed testing. You want to say that? Rigorous testing. What does rigorous testing mean? So I have a small request. See, we are meeting physically for the first time, and on the Zoom meeting, otherwise I know who is asking. Abhi, I do not know your names. So when you say something, can you also tell your name? कुछ के नाम मुझे पता है because we met at other times. But I'm sorry, I missed your name. Prince. Okay. हाँ. So what do you mean by rigorous testing? So what you are essentially saying is whatever test we do, it should be exhaustive. How long we do it is a different matter. But it should be exhaustive. It should activate all row decoders. It should activate all sense amplifiers. It should activate all memory cells. Okay. So now Talha is adding, we should also test at different PVT, like process to jo bhi ban gaya, but different voltages and temperatures also. Because the user specification involves a voltage operational range in which your system would work completely. So, okay, what else? Six Sigma. How will you ensure Six Sigma on silicon? Okay, so Deepank is saying we can stretch the memory to its limits, in the sense that we see what is the fastest that I can actually access the memory. So this is called as failure point testing. When does it fail? Can you always do it, Deepank? So he's saying only for test if you can do it, not for the regular industry standard product. Okay. What else do you want to test? We have to test every part before it ships. Are you okay? Are you okay getting a car which is not tested? No, you want everything to be tested, is it not? Every part should be tested before it is shipped. That rigor, that failure mode testing cannot be done on every die because it takes time. है ना? यहाँ पे सवाल था कि बहुत देर तक टेस्ट करना चाहिए. So for that we have accelerated life tests. We also have burn-in tests. We'll just look at that. What else? Accuracy. What do you mean by accuracy, Tala? Testing is that I stored a 0, I read a 0. That means it's fine. If it was a 1, it means it's a fail. So इसमें accuracy की बात कहाँ आई? तो fail ही हो गया ना फिर. Then if you stored a 0 and you read a 1, the memory has failed. इसमें accuracy क्या रहा? That's a failure. So do you mean to say that we should be able to tell a pass and a fail easily? Even a single bit failing, it's a fail. Suppose that single bit was to define whether it is an acceleration or a deceleration, and it has failed. You wanted to accelerate the car, it applied a brake. What happens? The car in the back hits you. You wanted to apply a brake because there was a person in front of you and it accelerates. What happens? And you behind bars. So not a single bit can fail. You do not know what every bit is being used for. Just one bit, na? One bit is the sign bit. That fails, and instead of accelerating, you decelerate, it's gone. So not a single bit can fail. You see? So as a designer, not a single failure. There could still be failures coming from somewhere else. They are not your responsibility. You see how to protect yourself from them also. As a designer, that is what your responsibility is. But, okay, you did not cause them. You saved the product from them. But you cannot say कि एक fail हुआ ना 1 million में से. Hello? Not acceptable. So I was giving a talk somewhere, and memory and yield. And I said, as a designer, we target 99.9% yield. He said, what's the point? And because there is all the point in targeting a 99.9% yield, because memories could be used in life critical situations. No, but memory yield is never more than 80%. And I understand, but that failure rate is because of the process. That is because of the defectivity of the die. At least due to design, there should not be a single failure. The design has to be robust, that it should not lead to even a single failure, because it is life critical. See, if there is some failure happening because of process, most probably your BIST and other things will be able to capture them very easily. First BIST run and you will be able to identify this memory cell is failing. The part is thrown away right away. However, if it is a design weakness, then what happens? Design weaknesses may surface, may come up at a particular PVT condition. So the dies that you are testing, if you not tested them in the extreme range of voltage and temperature, it could fail when incidentally such a situation arises, and you do not want that. So as a designer, your target is 99.99 whatever percent yield. So every company would give you some target. If you go to Synopsys, they will say 6.2 sigma, ST 6.4 sigma, someone 6.3 sigma, someone else 5.8 sigma, depending on capacity, process, application, the numbers may change. But that is what, as a designer, you have to definitely target. As a designer, you cannot say, oh, ek failure to chalega. No, can't. So, because it is about life critical operations, even if it is not about life critical operations, it is about user experience then. And if it is about user experience, then what we are saying is, that should also not get hampered per se. And that is where we still need to test. So what we will do is we will start to look at tests from two perspectives. We'll start to look at tests from two perspectives. One perspective is that of tests that you do on a tester. Another perspective is what all you need to do or design inside a memory so that that tester time is reduced. Why is tester time important? Do you remember? So the chip is ready. Let us say you are a cake bakery. You bake the cake. It's ready to be shipped to the customer, but it is not tested yet. Not tested means the batter has not been tasted yet. So you don't know if there is poison in there, or if by chance you miss to put some sugar or something. You're not sure about that. You can't send it out. It is ready, but you can't earn revenue from it. That is one aspect. Okay. What else? See, on one wafer, you may get hundreds of dice, hundreds of chips. And you want to ship them to a customer. Customer parts requirements would be of the order of, I want 1 million parts in 1 month. Let us say, example ke taur pe, huh? It's not a hypothetical situation. 1 million parts in a month is actually a small order. You would actually get much bigger orders. That's where the pricing of semiconductors is so competitive. Commodity products, you could have many more chips required per month. Let us say 1 million parts per month, passing parts per month. Let us say your yield is 90%. So how many parts would you need to test? Approximately 1.12 million. Approximately that many parts you will need to test in 30 days. 30 days means ditna many hours. Kitne many hours means per chip you will get some seconds to test. So that is the customer requirement, that your test time should be less than that. One aspect. Another aspect is you have a tester. Tester has a life of say 5 years. One tester costs $20 million, $40 million. Choose a number, whatever the cost is. If you're able to test 100 dice on that tester in those 5 years, what is the cost per die of the tester? That 40 million gets amortized over 100 dice. So आपकी per die की test cost ही $40,000 से ऊपर है. 40,000 ज़्यादा. $400,000. See, per die 400,000 rupees is the cost of the tester amortized on it. So obviously not a real case. Let us say 1 million dice you're able to test in 5 years. So what is the cost per die? $40 per die. $40 per die. मतलब absolutely unacceptable ना. आपका जो एक सेल फोन है उसके अंदर एक जो चिप होता है, एप्लीकेशन प्रोसेसर होता है, that is sold for something like $10, $8. बिल्कुल हाई एंड होगा तो $20. That kind of stuff. So test cost cannot be so high. So you say, okay, I have to test not 1 million, but 100 million. So 40 cents. Something like that. So I want to reduce the cost. The time that you spend on the tester has a direct bearing on the cost, has a direct bearing on your profits. And the longer the test, the more your product becomes obsolete before going to the market. So you want short test duration. So while we want everything to be done, tested and done exhaustively, we do not want to give a lot of test time. What does this mean? We need to be smart. We cannot actually test each and every element separately and say ki kuch hoga. We have to test in parallel. We have to test only those vectors which will sufficiently inform me that there is a failure. कहने का मतलब, I can actually, if there is a 10 input memory, I can actually have 1000 vectors there, 2 raised to power 10. 1024 vectors are there possible. I want to somehow identify only those 40 vectors out of these 1024 which are sufficient to tell if the memory is functional or not. Memory nahi, aapka chip is functional or not. What we also want to do is, for example, for memories, if you start to access every memory location from the tester, what happens? How many locations could there be? If there are 64 megabit memory on chip, 64 million locations. A tester would operate at, the IO of the tester would operate at 10 megahertz, 20 megahertz, 50 megahertz. 50 megahertz, 64 megabit memory. Every location needs to be tested. How many cycles? So a few seconds in just one read write of the memory. So what happens? You want to test 20 vectors or 20 patterns, 20 into whatever this is. So overall, आपकी खाली पूरे chip में खाली memory test करने के लिए you end up wasting tens of seconds, 20s of seconds. Again, unacceptable. So for such circuits, what we have is called as built-in self-test. As soon as you power up, you will trigger built-in self-test. Now this built-in self-test, because it is on chip only, it is not limited by the tester bandwidth. It is limited by the frequency of your processor or the controller. And it can actually run at the maximum speed prescribed by the memory, approved by the memory. So instead of operating at 50 megahertz, you're now able to operate at 500 megahertz or even 1 gigahertz, 2 gigahertz, depending on how big or small the memory is. And you're not going off chip again and again. You're just testing right there. The controller is right there. And this significantly reduces tester time because you're not engaging the tester. Tester you engage only to get the trigger signal and then finally to tell whether it's a pass or a fail. So memories have what is called as BIST, built-in self-test associated with them. So now when you want to associate such on-chip components with the memory, there would be some design changes that you would do to the memory itself so that this testability is enhanced, so that the number of vectors that we need to test the memory can be reduced, so that the overall test time and test cost can be optimized. And that is what is the second part of what we will be discussing. First part is what kind of vectors, what kind of tests. Second part is what kind of design infrastructure to be embedded inside the memory so that you are able to test and debug the memory. Both are important. That is repair elements. That is not testability. That is only something failed, I am repairing it. Redundant column and redundant row. Yes, you have to test to identify which part is failing. That is a part of this testing. आप पता लगाओगे क्या फेल हुआ, उसके बाद आप ट्रिगर करोगे रिपेयर मैकेनिज्म. जब तक पता ही नहीं what has failed, how will you repair? What will you repair? So that testing happens, then you repair, then you test again, and then you ship to the customer. So what are the possible error locations inside a memory? Errors can happen everywhere. They could happen in the storage elements, bit cells. See, bit cells are the only parts in a memory or in a chip where you use those long contacts, you remember? So bit cells are also the high density parts. Lots of DRC rules are violated. As soon as you do that, what happens? There's a high probability of failure. That is why in the first place you added those repair elements, because you knew that bit cells could fail. That is why you said I will have an extra row or an extra column in place. Because you knew I have violated lots of rules over here. Something could happen. Let me prepare for it in advance. So failures could happen everywhere. They could happen in the sense amplifiers. They could happen in the they could happen in any part of the memory, column decoders, anywhere they could happen. And what kind of faults can happen? There can be open faults. That is, you wanted a wire to run straight, but there was a break in between. You wanted a VR to be somewhere there, but the VR got faulty. It is not really connecting the metal 2 with the metal 1. So there are opens. There could be shorts. That okay, two wires were running close to each other. Some defect happened. Shorting happened. You wanted to put a 0 somewhere. Now 1 goes. You wanted to have a dynamic signal there, but it is now stuck at 1 or stuck at 0. Whatever. Anything can happen. Decoding faults. Similar errors happening inside the decoding array, decoding region, where one particular row is simply not selectable. Let us say row 28 is not selectable. Or you give one address, but 10 rows get selected. Multiple word line selection. That can also happen. It could be because of some logic error at your end. You designed it wrong. Or it could be because of some error in the, say, pre-decoding region, where due to something, simultaneously pre-decoded line 0 and pre-decoded line 8 were getting selected. Could happen. Some fault. And multiple word line selection could happen. So address decoder faults. Then there could be pattern sensitive faults. What do you understand by pattern sensitive faults? It could be due to coupling. It could be because of the fact that, okay, now one bit line is expected to discharge, but the other one is expected to be held at 1. If this one discharges at a very fast rate, it could couple, and this one could also go down a little. In places like ROMs, DRAMs, where you have very dense cells, or flash, where you have very dense cells and bit lines are right next to each other, this becomes a bigger problem. In SRAMs, bit lines are still farther away. There are also VDD lines and ground lines running in between them. But in flash, ROM, and DRAMs, just bit lines, and all placed right next to each other. Coupling faults, which could be pattern sensitive. Sense amplifier faults, you are expected to, read a 0 in between. So a string of ones, a big string of ones, and somewhere in between you wanted to read a 0. But it doesn't happen. You see, you had a 0 in between there. But because you were reading all ones, somehow you tend to read 1 again. And there's a failure. So things can happen. DRAMs, refresh period. Aapne expect kara ki the refresh needs to be every 300 milliseconds. But actually it was required to be 250 milliseconds for a few cells. So those cells will fail. So in terms of tests, as we already discussed, we need very good coverage. Every part of the memory, whether it is storage array, or it is sense amplifiers or column decoders, every part can fail and every part should be tested. And it should have just reasonable time complexity. It cannot be something to the power. It cannot be something to the power, n or something like that. Because otherwise, kya hoga? As soon as the memory size increases, your test time would simply explode. So you don't want that also to happen. So the order of your test pattern, the order of your test program should be simple. It should not be very complex. So typical tests that we have are solid patterns, that is entire array is 0 or entire array is 1. Checkerboard patterns, alternate cells are storing 0 and 1, so that you can also see some coupling effects also in there. All array 0 or array 1 is also a very good pattern, because you put everything at 0, just write 1 in one cell and see if you can read it correctly. This is a very strong. So solid zeros and checkerboards, they are two most basic patterns which always have to be tested, and they will screen out a huge majority of faults in the memory cells. Okay. Then you come to March tests. March test means that you have a background pattern You initially background the memory either with a checkerboard or a solid pattern, and then every location one by one you go, kind of you're marching through the memory. That is why it is called a march test. You're marching through the memory. Every location you're writing a 0 or a 1, reading it, then writing back again. Okay, or writing the original data back again. This kind of tests are the most commonly used tests for memory testing. आप जब भी BIST की बात करेंगे तो you will hear the term of march test. What is the order of your march test? So order of your march test means how many times do you need to access every memory location to be able to test exhaustively. So if it is a 10n pattern, it means that every memory location is accessed 10 times. So if the memory size is something, you know that this is the test time required. If the memory size is halved, you know the test time would also reduce to half or something like that. Now, you would usually want march patterns where you just go in this manner, linear manner, so that the order is n. Order is n. There are also these galloping tests. Galloping tests means that so march में हम क्या कह रहे थे? I put a background pattern. I write something into I write a different data into a pattern, into one particular memory cell, read that. If it is fine, I go move forward. Or if I write back and then I move forward, that is march. Galloping is, there is a memory, I put a background data in there. I change content of one particular memory cell. And now I read not just that particular memory cell, I read the entire memory. So the order of this test is n square. And it is impractical today. It is not used. It can possibly point to some other fringe errors which could happen, but it is impractical to use that kind of a test pattern today. And what that means is we need to define either new test patterns or be much more exhaustive in our regular testing. I'm sorry? Not required. You will not be using them. Just be aware there is a galloping test where when you change contents of one memory cell, you still validate that contents of all the other memory cells were fine. So consider a 64 megabit memory. You change one bit and you're testing 64 megabits again and again. No point. So if you really need to do something, what could be is that, somewhere a mix of galloping test and march test. आप एक लोकेशन को लिखो, then उसके आसपास की 8 locations को टेस्ट कर लो. Neighborhood pattern sensitive. We will look at neighborhood pattern sensitive tests. So those would then practically cover your entire gamut of faults that could happen. Galloping tests otherwise are simply impractical. If you do galloping tests, then you do not need NPSS that we will just talk about. So this is march test. As I mentioned, there's a background pattern. You change contents of one cell, test that cell, whether it has been written correctly. You write back again the original pattern and you move to the next location. So this is how you march. And this is where the number of steps involved here defines n. Okay, so write 0 in every cell, n steps. For I is equal to 0 to n minus 1, do this. So there are 3 into n there. And then again, n over here. So all of this, you will see that lead to 8n kind of a thing. Or for every pattern, you will be able to identify what is the number of times every cell is accessed. As we already discussed, we have to test for all voltage temperature combinations. Hello. So we have to test for all voltage temperature combinations. We have to test for operational limits. We have to test for what is also called as RAM sleeping sickness, where if you have not really written into the DRAM for a long time, due to leakage, there could be failures. So refresh rate ka issues jo hote hain. So those things also have to be tested. During production, you also do what is called as a burn-in. What does this mean? That for a very short duration, every die, we put it through high temperature and high voltage testing, but for a very short duration. It is not an accelerated test. So it is not an accelerated live test, though it is an accelerated test. What it does is, you've heard about the bathtub curve? You have, I have told you. What is a bathtub curve? When we were doing testing, we saw that this kind of a curve exists. Yaad hai? What does this mean? This means that over here, this is failure rate. And this is time. So initially, the failure rate is high. So what happens? Initially, when the product goes to the market, lots of parts would come back. Parts which have not failed for this initial period will usually continue for a long time. And then the failure rate at once starts to increase again, which is due to normal wear out mechanisms. So as a designer or as a validation engineer, what you want is, you want that before you ship out any chip, you should have at least this kind of aging done. And then you test the memory again. This is called as burn-in. That every part is subjected to some high voltage and temperature testing for a very short duration, so that initial 2 days or 3 days of lifetime is exhausted within 10 seconds, within 5 minutes, whatever. Actually, very short duration. And then when you test the memory, or then you test the chip, you will be able to kind of replicate all those early life failures. So these are called as early life failures. Something tricky is happening today. So these are called as early life failures, and you want to kind of capture them, identify them, and remove such parts from the product cycle right away. So just give me a second. My screen is working fine. The recording is coming along fine, but the projector is not showing it for you. Hello. So next, what we do is we check output leakage current. Why is this test important? We already talked about it in a little, but why is this test important? Leakage current test, also called as IDDQ test. Any ideas? This is one of the first tests that you do on a chip. So come to think of it, there could be some errors which could be there in the IO region of the chip, not your memory, but of the chip. So what do? You want to supply a 0 node. You want to supply You want to drive something from the memory or from the chip or to the chip, but there is a short there. As soon as you apply a voltage, you will see that a high current starts to flow. This indicates that the chip has some VDD or ground short somewhere. So even before you do any other testing, you actually would do IDDQ testing. Because if there is some such error and you start to do regular testing, what happens? Your tester will blow up, because this would start to sink so much current that it is unacceptable. So in a very controlled setting, you say that, okay, I want to see that no input should consume more than, let us say, 1 milliamperes of current. And if there is some pin or something where more than that kind of a current is used, then we say that this is a failure. Those dies are rejected. That is called as IDDQ test. What do we do? Just give me a second, then I will need to call them up and BIST run as self-test, yes. BIST is not available for all the entire chip. No? BIST is available only for the memories. So I'm not talking about only memory test. Test is, you have to test everything there. So you have to test everything, then you have to test everything. What to do? Just give me a second. So IDDQ test you will need to do so that you're able to identify whether there is some IO failure or some VDD ground short happening somewhere, so that if it does happen, you do not waste your time testing this chip, because if there's a VDD ground short, there's no way to recover it. Then another test that you do on memories is what is called as a voltage bump test. Now, what happens in a voltage bump test? In a voltage bump test, you give you for example, on a DRAM, you want to put one particular data onto the memory, and you increase the voltage by little amounts. Okay, and then it could happen that because of some coupling or something, the contents of the DRAM cell are lost. So you raise the voltage and you see if the reliability and if the leakage and everything is in place or not. Because as you increase the voltage, what happens? Leakage also increases. So you see that if we give a voltage bump to the memory, are there some failures that can creep in? That is voltage bump test. Then we have AC parametric tests, where you simply bias the voltages or operate the system at different supply levels at different temperatures and see the frequency at which the system would fail. Okay, that is the parameter. That is now beyond the functional testing part. You realize we started with the functional testing, IDDQ testing, voltage bump testing. They're all simple functional testing. Now, when we come to AC testing, we are talking about testing across different voltages and seeing that the memory is actually operational at the frequency it was expected to be operational at. Wow, Jadu. When he will come, he will have no, like, there is no problem here now. What do I tell? So, this talks about all the delays and everything in there. Then access time tests. You want to characterize the memory, see that, you know, the speed at which you expected the Q on the output, it is actually there at that speed. And you also have, so in advanced technologies today, you also have what is called as built-in self characterizers. So one is built-in self-test, where you test the memory and this controller will activate every row, every column, everything, and everything would be fine. There are also built-in self-characterizers which would characterize the access time of the memory or different parameters of a PLL, for example. So this is called as BISC, B-I-S-C. BISCs are not typically used on production chips. They are used on test chips only. But on-chip testing for access time is also possible. And for very performance critical applications, you may see that a particular company would want a light BISC. Light BISC means only access time testing, no setup time testing, or only hold time testing, no other testing. Some such functionality on chip also, along with the BISC. That time is not far away. If it is not already here, it is not far away. It will happen. ठीक हो गया, मैं इनको यही कह रहा था. अब तुम आओगे यहाँ पे सब कुछ ठीक दिखेगा, लेकिन बीच में गायब था. तो कुछ ग्लिच है कहीं पे. देख लो. आई होप दोबारा से ना जाए, लेकिन वेट करके शायद कुछ पता लग जाए. नहीं तो यू विल आल्सो हैव टू अटेंड मेमोरी क्लासेस, अखिलेश. Okay, so other is running time tests like alternate zeros and ones are stored in the memory, and you just see that every 0 and 1 is tested and everything. But all of this actually, see why I'm saying all running time test, this test, that test, you will realize that all these have to be taken care of in your march patterns. The march patterns that you build, the test patterns that you build around your memory testing, they have to include all these kind of patterns. They have to include everything like this so that in the minimum test time, you're able to still test the memory completely. Sense amplifier fault test, जैसा हमने कहा इतने सारे string of ones था, बीच में एक 0 read करा, फिर वापस ones read करा. So something like that should be used for testing sense amplifiers. So patterns should include such kind of testing also. Now we come to what is, see, we said that we will no longer do galloping tests. The order is so high that you cannot afford to do them. But we still need to see if when I wrote something here, something else changed elsewhere, I want to still capture such kind of faults. So such kind of faults are called neighborhood pattern sensitive faults, NPSF. What does that mean? I changed something in this, the neighborhood got impacted. Or I did something in the neighborhood, this cell got impacted. So if I have to test the cell in its completeness, I have to test all the neighboring cells, change all the neighboring cells and see the impact on this cell. But just these neighboring cells and this cell, that is sufficient. I do not need to go to entire memory read. How many neighboring cells we have? 8. Depending on my pattern, 8 reads extra honge, na ki 64 million. So the order of magnitude of the test is still order n, not n square. And that is where NPSF are complex patterns, reasonably complex patterns, which are applied to reduce the overall test cost. See, galloping test would cover everything, but order is n square. Test time is huge, not acceptable. So we as designers have to identify other tests which could be able to capture all those faults. So there are different kinds of NPSF. Passive NPSF, active neighborhood pattern sensitive faults, active and passive, and static. What is the difference between them? Passive means मैं तो यहाँ बैठा था, कहीं पे कुछ हुआ या कहीं पे कुछ नहीं हुआ. Pattern आसपास कुछ लिखा था जिसकी वजह से लीकेज हुई, जो भी हुआ, the contents got corrupted. That is passive. Active means I was sitting, something happened in the neighborhood and the contents got corrupted. Active passive means that सब करके देखा था. Active passive means that I was sitting, something happened, only when the remaining pattern was like this fault appears. Only when everything else was 0 and I wrote a 1 in this particular cell, my cell content got corrupted. When there was even a single 1 in the neighborhood, there was no corruption. That could happen. because of some bridge faults, some shorts, some opens, such kind of a sensitivity could be there. So we need to be aware about that and we need to take care of that. I have a clue why it could be happening. We class के 5 minutes बाद let us discuss. अभी रुको तुम यहाँ पे 5 मिनट और मैं बताऊंगा, फिर हम debug करेंगे क्यों हो रहा है ऐसा. So active passive neighborhood faults and then static neighborhood faults. Ki, again, I did some change at a very slow pace due to leakage, something is happening or something, you know, that kind of stuff. So all these kind of faults can happen. And for that, you could have different kinds of patterns that could come into picture. Yeah, you know, cell's ability. क्या करें? कनेक्टर का इशू नहीं होगा शायद. कुछ तो हो रहा है. कुछ ज्यादा हो गया. कंफ्यूज ही आ गया है, कंफ्यूज ही आ गया है. बताओ पर कुछ हो. अब कंफ्यूज ही आ गया ही है तो हाँ देखो कुछ हुआ. मैं रीस्टार्ट करता हूँ पावर पॉइंट को, फिर होगा, देखते हैं. नहीं आ गया आ गया आ गया. क्या? यूएसबी भी है वैसे, बट टाइप सी से ही ज्यादा अच्छा रहेगा. हाँ करो. So in context of neighborhood pattern test, sensitive test, there is also a concept of what is called as deleted neighborhood. Deleted neighborhood means essentially those cells in the immediate neighborhood of the memory cell that you are putting under test, which could be causing an error on the base cell. So base cell is the test cell, the cell that you are interested in, and deleted neighborhood means the neighborhood in which there could be an immediate, in which could lead to an immediate error. So typically deleted neighborhood for a pattern could mean those in the same column or those in the same row, adjacent cells in the same row or the same column. Why? Because the cell right up there shares the bit line contact. shares the VDD contact. The cells which are adjacent, they share the word line contact. They share the ground contact. So typically, that is what the deleted neighborhood is. And if you're able to test this deleted neighborhood, it should be good enough. But there could be some complex patterns. So there could be some complex patterns where the error could actually happen in the diagonal cells also. So they also become a part of that deleted neighborhood. So there could be some patterns which could be relevant for one type of tests, type 1 active NPSS, and there could be other deleted neighborhood for type 2 NPSS. And the reasons could be different. So this, when we say that the diagonal cells could also be important, why would that happen? What is shared across the diagonal with the diagonal cell? Which contact exists there? SRAM cell layout. What is shared at the corner of a memory cell? Ground. Because ground is shared with the adjacent, all the 4 cells. So the diagonal cell also becomes relevant. Even though we would think that vertical and horizontal, that is good enough, but because there is a sharing that is happening across a diagonal cell also, the cells in the diagonal, those 4 cells also form the deleted neighborhood there. Okay. Now you understand why it is important to understand the layout when you define patterns. If you do not understand the layout, you could miss out on some failures that could actually happen on silicon. Yes. Whatever it is. If you are, suppose you are using a dual port SRAM or a ROM or something like that, the sensitivity to deleted neighborhood is very, very high because of coupling, because of so many other reasons. In a typical SRAM with differential read-write operation, deleted neighborhood is not really very important. But in DRAMs and what do you say, dual port or multi-port SRAMs, in ROMs, this deleted neighborhood is very important and you will need to do this kind of testing. Luckily, those memories are not as huge. SRAMs are typically 64 megabit, can be 64 megabit. DRAMs can be, but okay, DRAMs तो off chip ही होती हैं usually, तो उसका अलग testing कर सकते हो आप. On chip में dual port memories, ROMs, they're usually very much smaller. So even if you have to do more rigorous testing, overall impact on test time is limited. SRAMs, you will not really go to rigorous NPSF testing. 1 or 2 NPSF kinds of NPSF you will test, good enough. And that too, you will try to somehow complete it within the March tests that you already were defining. Okay. So different kinds of NPSF. Now, what is very important is when you are writing those test patterns, which test should you do first and which test should you do next? Why? Because that would define the shortest route through which you could cover all the nodes, all the kind of tests that are possible, which route to follow. So you would make this kind of graph and see, I could go from here to here, and you see how to traverse these graphs. And that is the part of pattern design for BIST. What pattern should BIST run in which sequence so that you can actually test in 7n instead of 10n. Tester time is very important. So how many of you have done course on graph theory? Studied graph theory in one of the algorithm courses or something? Traveling salesman's problem? Sounding like Greek to you, huh? So see if you can, like if you want to go into EDA design, that is, or say BIST design or algorithmic design, once you join a job, at least pick up a course on graph theory and study it. Coursera would have it, even if you've not done it in IIIT yet. That could be a very relevant course to do if you are entering into this kind of a job, because how to traverse this graph in the shortest possible time is an important problem. Okay. So once you have that, you also look at, what changes do you need to bring about in different neighborhoods? How do you tile them? And there is this entire different kind of group. You don't need to learn this. ये रट्टे मारने की जरूरत नहीं है. This is just to share with you the complexity involved in designing test patterns. Okay, so don't get overwhelmed कि ये क्या है deleted neighborhood और ये सब. Okay, I may ask you a concept around deleted neighborhood. मैं नहीं पूछूंगा, कोई इंटरव्यू में पूछ सकता है कि आपने मेमोरी डिजाइन टेस्ट का कोर्स करा. What is deleted neighborhood? So you should know what a deleted neighborhood is. Why is a deleted neighborhood a set of either just the 4 cells or all the 8 cells? Why are all the 8 cells there in picture at all? So you should know all these concepts. Don't need to learn about ये A, B, C, D. ये बस दिखाने के लिए है कि when you design the test, all this needs to be accounted for, and you will have to define patterns very carefully. It is not just कि हाँ मैंने 0 लिख दिया और 1 लिख दिया और हो गया. Because there is a constraint on how much test time we can do. There is a very big constraint on how quickly to do the test. What is the minimum number of patterns with which you can do the test? There are these problems that need to be solved. Okay. And there are different kind of algorithms. You see, complexity of algorithms, as soon as you start to cover more and more NPSS, look at this over here. We're talking about 512 to N. You're talking about 569N. So because we want to cover many test patterns, many neighborhood pattern sensitive faults, we would need to run so many extra cycles. But you don't need to use them for every kind of memory. Only for those memories where you suspect this could happen, those technologies where you suspect this could happen, you would do that. Okay. And then in this also you see how to optimize, how to minimize. Can you reduce 1000? So if you reduce 1000, you're still 20% faster. Something like that. So I think we should close here. Next class we will start with testability infrastructure inside the memories. That's a completely different independent topic. We'll start from there in the next class. Any questions till now? पूछ लिया बीच में. Safety features, yes. How we can test safety features? उनकी testability अलग होती है. We will talk about it in the next class. So you have to ensure that safety features are also testable. So abhi, all of this could be Greek to others because safety features no one else knows yet. We'll discuss about safety features in all the next classes. You will know about it then, don't worry. But whenever you add any feature, how to test that feature is something that you have to think right away. You will see that this is more and more emphasized when we discuss infrastructure, testability infrastructure inside the memory in the next class. Okay. So if it had a 0 already and you write a 0 again, can you observe any difference?
That is the point. Like if we are always writing opposite data, then we are reading and feel that it is, but it is possible that it is.
Yeah. So what we do is we do the same thing for 0 and for 1. We do it for both the sides. So that if there is a tendency to flip towards 0, then we know when we are trying to read a 1. Anything else? Okay, so we have recorded this session. We will put it on YouTube, don't worry.